The single biggest mistake new 3D printer owners make when they sit down with an AI design assistant is asking for things in the wrong vocabulary. The model already knows every modeling technique, every slicer setting, every assembly trick. It has read every Bambu wiki page and every Prusa knowledge base article. The bottleneck is not the model. The bottleneck is that you have to be able to name the technique you want in the words the field actually uses. If you ask the assistant to make your part stronger, you will get vague suggestions. If you ask it to increase the wall count from 2 to 4, add a fillet to the internal load-bearing corners, and switch the infill to gyroid aligned along the load path, you get a real, specific change you can print. Today I want to give you that vocabulary. Before we dive into specific words, let me give you the map. 3D printing vocabulary lives in 3 roughly independent layers, and the AI agents you are talking to use words from all 3 depending on what you need. The first layer is the software layer, where words describe how the geometry is represented inside the modeler. The second layer is the design layer, where words describe how the part will physically behave under load. The third layer is the slicer layer, where words describe how the printer turns the design into actual plastic, layer by layer. Today we will spend roughly equal time in each layer. Each slide teaches 1 or 2 specific words, with the wrong way to ask for it next, to the right way to ask for it. By the end of the video, you will know how to phrase almost any design request in language the AI already speaks. The first vocabulary distinction is between a mesh and a solid. A mesh is a surface made of triangles, which is what an STL file holds and what your slicer eats. A solid is a mathematical description of a shape made of curves and surfaces with exact geometry, which is what tools like FreeCAD and Fusion 360 produce. The difference matters for one practical reason. If you tell the AI to model your part in Blender as a mesh from the start, you can never go back and say, change that hole from 6 millimeters to 7. The dimensions are baked into the triangles. If instead you tell it to model the part as a parametric solid first, then export to a mesh at the end, you can come back and tweak any dimension, and the geometry regenerates around your change. Always start. The single most important property of any 3D model that you intend to print is whether the mesh is manifold. A manifold mesh has every edge shared by exactly 2 faces, no more, no less, which together form a closed volume. The everyday word for this is watertight. If you poured water into the mesh, none would leak out. The reason this matters is that the slicer needs to know what is inside the part and what is outside, and a non-manifold mesh with stray triangles, internal or tiny holes between vertices breaks that distinction. Either the slicer refuses your file outright, or worse, it silently fills solid where you want it hollow. So when you hand the AI any model to modify, the first thing to ask is, please verify the result is a manifold and watertight mesh with no internal geometry or self-intersections before The next word is topology, which sounds intimidating, but just means the layout of vertices, edges, and faces in your mesh. There are 3 kinds of faces: triangles, which is what slicers want at the end, quads, which are 4-sided and the modeler favorite, and n-gons, which are 5 or more sided, and a polite signal that something is wrong. The reason topology matters comes up the moment you ask for organic, smooth shapes. The smoothing modifier in Blender, called Subdivision surface, only behaves cleanly on a quad-dominant mesh. Pass it a mesh with triangles or n-gons, and you get pinches and dents at the spots where the mesh is uneven. So when you ask the AI for, say, a smooth grip on a tool, you should specifically ask for clean quad topology with even edge flow, then apply subdivision surface, then triangulate before export. Every face in a 3D mesh has a property called the normal, which is just the direction the face is pointing outward. When normals are flipped, the rendered preview shows the face going inward instead of outward, and the result looks like a black hole or a missing patch. More importantly, the slicer also reads normals to figure out which side of the surface is the outside of the part. If the normals are wrong, the slicer can lay plastic on the wrong side of the wall, and you get unprintable junk. The fix is one menu item or one Python call. The fix has a name, which is recalculate normals outside. So whenever you hand the AI a model that came from somewhere else, especially a downloaded one, ask it to recalculate normals outside before doing anything else. The single most powerful set of operations in any modeler is the Boolean trio, named after George Boole, the logician. Union joins two solids together into one bigger solid. Difference subtracts the second solid from the first, leaving a hole or a notch in the shape of whatever you subtracted. Intersect keeps only the volume where the two solids overlap, which is rarer but useful for cutting one shape with the contour of another. Almost every functional part you will ever print is some sequence of unions and differences, often dozens of them in a single design. The vocabulary win here is huge. Instead of saying, cut a hole here, you can say, Boolean difference, a 6 mm diameter cylinder centered at this point, extruded 8 mm into the part. The AI knows exactly what to do. 2 words you absolutely have to know if you ever want a part to survive use are fillet and chamfer. A fillet is a curved blend on an edge, smooth and rounded like the corner of a smartphone. A chamfer is a flat cut on an edge, like a 45-degree bevel, like the edge of a plate. They look similar, but they are not interchangeable. Internal fillets distribute stress, which means a part with a sharp internal corner cracks along that corner under load, and a part with a fillet does not. So load-bearing internal corners always get a fillet. Chamfers, on the other hand, print better on downward-facing edges, where a fillet would sag because the printer is laying plastic in midair. So when you ask the AI for stronger parts, name fillets specifically, and chamfer the downward edges. A small but useful concept that newcomers almost never name is the draft angle. A draft angle is a slight taper on what would otherwise be a perfectly vertical wall, typically 1 to 3 degrees off vertical. The reason draft angles exist is that injection molding parts need to release cleanly from the mold, and even on a printer, they make outer walls look cleaner and reduce the elephant foot flare you get on the first layer. A perfectly vertical wall is a beginner tell. Designers in industry add a small outward draft to outer walls and a small inward draft to whole walls almost reflexively. The vocabulary win when talking to the AI is, instead of just saying, make the box look more professional, you can say, add a 2-degree outward draft to all outer walls and a 2-degree inward draft to the inside of the screw bosses. If you have ever printed 2 parts that were supposed to fit together, and one of them either fell apart or seized up like cement, the word you needed was clearance. Clearance is the deliberate gap between 2 parts that have to mate, and the right number depends on the printer. On a Bambu printer, a sliding clearance fit is around 1/5 of a millimeter of gap. A press fit is around 1/10 of a millimeter, and a loose fit is around 4/10. Without naming the number, the AI guesses, and the guess is wrong roughly half the time. Always specify the clearance. The other vocabulary win here is the chamfer. Always chamfer the lead in edges of mating parts, because a sharp lead in catches even when the clearance is right. So a good prompt is, design the peg with this clearance for a sliding fit and chamfer both lead in edges. The most important geometric constraint in 3D printing is the rule that an overhang steeper than 45 degrees from vertical needs supports. An overhang is just a downward-facing surface that has nothing under it. A well-tuned Bambu printer can actually push past 45 degrees, sometimes to 60 or 70, but 45 is the rule of thumb that always works. Below that angle, each new layer of plastic has enough of the previous layer underneath it to bond and stay in place. Above that angle, plastic droops into open air. A bridge is the related concept, which is a flat horizontal span between two supports. Bridges of about a centimeter print fine if the cooling fan is aggressive. The vocabulary win is, instead of saying, make sure it prints, say, design with no overhang past 45 degrees, and bridge any horizontal span up to 1 centimeter. When the geometry breaks the overhang rule, the slicer can add supports, which is scaffolding plastic that holds up the overhanging surfaces and gets snapped off after the print. There are two main flavors. Linear supports are a brute force vertical grid, which is ugly and uses a lot of material, but is dead reliable. Tree supports branch up from the bed, like real trees, use far less material, leave fewer scars on the part, and look much cooler in the slicer preview. The Bambu Studio default for organic shapes these days is the tree supports, but you can pick. There is also a setting called the interface layer, which is a denser cap between the support and the model. Without an interface, supports peel cleanly. With one, the support side surface is smoother but harder to remove. Name your preference when asking the AI to design a print-friendly part. Two slicer words you absolutely have to know are layer height and layer width. Layer height is the vertical thickness of each printed layer measured along the z-axis, and it controls how visible the layer lines are on the side of your part. A common layer height for visible surfaces is around 0.12 of a millimeter, which is fine and smooth. A common layer height for hidden geometry is around 0.20, which is fast. Layer width is the horizontal width of each line of plastic, controlled by the nozzle diameter and a small multiplier. Most prints use a width slightly bigger than the nozzle. The vocabulary win is you can ask the AI for variable layer heights. Instead of one global setting, you can say use a fine layer height on the visible top surface and a coarse layer height on the hidden infill regions to save time without sacrificing the look. Infill is the internal lattice of plastic that fills the inside of a solid part, instead of printing the part fully solid, which would take forever and waste plastic. There are two settings to know. Density is the percentage of the inside that is actually plastic, with most prints in the 20 to 40% range. Pattern is the lattice shape. Gyroid is the strongest in every direction and supports its own top layers. Haitian comb is rigid but slow. Lightning uses minimal material to support only the top, which is fine for cosmetic parts. The biggest secret of 3D print strength is that walls matter more than infill. The number of perimeter walls around the outside of the part is the actual strength knob. So instead of cranking the infill, ask the AI to bump the wall count from 2 to 4 and leave infill at 30% gyroid. The top of a printed part is where most of the visible quality lives, and there are 3 vocabulary words that change the result. Top layers are the solid layers that cap off the infill at the top of a part, usually 4 to 6 layers thick to bridge over the infill underneath. Ironing is a slow second pass with a hot nozzle, with no plastic flowing, which polishes the top layer flat and almost shiny. It adds time, but the result is striking on flat tops. Fuzzy skin is the opposite. It deliberately roughens the outer walls into a textured surface, which hides layer lines and adds grip, and is great for handles and grippy cases. The vocabulary win is, instead of asking for a smoother part, you can say, increase top layers to 6 and enable ironing, or enable fuzzy skin on the outer walls of the grip area only. Adhesion is the printer word for the part sticking to the build plate, and 3 words describe the 3 ways to help. A skirt is a thin loop printed around the part, not touching it, just to get plastic flowing through the nozzle before the real print starts. A brim is a thin flange added to the first layer of the part itself, around 3 to 5 millimeters wide, which gives warpy materials more contact area with the bed and reduces the chance the part lifts off mid-print. A raft is a full disposable platform printed underneath the part, used in hard cases like nylon or large ABS prints. Each of these costs material and time, and they are not interchangeable. So instead of saying, make sure it sticks, you can say, add a 5mm brim to the bottom of the warpy outer wall. 2 words for the visible quality details that make a print look professional or amateur. Stringing is the spider web of thin plastic threads that appears between features when the nozzle drags hot plastic across an open gap during a travel move. The fix is called retraction, where the nozzle physically pulls the filament back a few millimeters before traveling, so the molten blob inside the nozzle does not ooze. The Z-seam is the vertical scar that runs up the side of every printed object, where each layer's outer perimeter starts and ends. Bambu Studio can hide the Z-seam on a corner, randomize it across the layers so it looks like noise instead of a line, or align it on a specific back face. Vocabulary win. Instead of saying, fix the lines on the side, you can say, align the Z-seam on the back face that nobody will see. The right filament is half the design decision, and 4 material names cover almost every use case. PLA is the default. It is easy to print, stiff, has very low warp, and is great for prototypes and display models. Its weakness is heat resistance. A part left in a hot car will deform. PETG is the next step up. It is tougher than PLA, has a slight flex, is water resistant, and works great for outdoor brackets and food adjacent containers. ABS is the engineering plastic that you see in car interiors. It is heat and impact resistant, but it warps badly without a heated enclosure, and it smells. TPU is the rubbery one. It is flexible, measured by shore hard, and used for gaskets, bone cases, and tires. The vocabulary win is naming the material in your prompt, so the AI tunes the design for the material's strengths. There is one word that explains 9 out of 10 mysterious print failures, and the word is hygroscopic. A hygroscopic material absorbs water from the air over time. PETG, TP, and polycarbonate are all strongly hygroscopic. PLA is mildly hygroscopic. Wet filament prints with popping or crackling sounds, blobs and oozing on the surface, rough top layers, and weak bonding between layers. The fix is a filament dryer, which is essentially a small oven that holds the spool at 60 or 70 degrees Celsius for several hours to drive out the water. The reason this word matters for AI-assisted design is that the AI cannot tell from a slice preview whether the filament is wet. So when you ask the AI to debug a print quality issue, the first question to teach it to ask is your filament hygroscopic, and have you dried it recently? For Bambu Lab printers specifically, 3 more words round out the vocabulary. The AMS, which stands for Automatic Material System, is the 4-spool changer that enables multicolor and multi-material prints. The vocabulary win here is naming the filament slot in the AMS so the AI can write the right color map. A plate refers to the magnetic build plate that the printer prints on. The 2 common plates are the cool plate, which is for PLA and needs a thin layer of glue stick, and the textured PEI plate, which works for PLA, PE, and ABS without glue and leaves a matte finish on the bottom. Finally, 3MF is the Bambu native project file format. Unlike STL, which carries only triangles, a 3MF file carries the model, the slicer settings, the plate type, and the AMS color map all in one file. Always share 3MF, not STL. Now let me put it all together with 5 concrete bad to good prompt rewrites that combine the vocabulary we just covered. First, instead of make it stronger, ask increase the wall count from 2 to 4 and add a fillet to the internal load-bearing edges. Second, instead of fix the overhang, ask, rotate the part so the overhanging face is below 45 degrees from vertical, or add tree supports touching the build plate only. Third, instead of make it smoother, ask, reduce the top layer height and enable ironing on the top surfaces. Fourth, instead of make the peg fit the hole, ask, design the peg with a sliding fit clearance and chamfer both lead-in edges. Fifth, instead of fix the broken model, ask, recalculate normals outside, remove non-manifold edges, and convert n-gons to quads before exporting. Notice the pattern. Every good prompt names a specific technique with a specific number. If you remember nothing else from this video, carry these 5 ideas forward. First, vocabulary is the AI design assistants you have access to today already know every modeling, slicing, and assembly technique that exists. The only question is whether you can name what you want. Second, manifold and watertight are the 2 words that decide whether your file even slices. Always verify them before exporting. Third, the actual lever for stronger parts is the wall count, not the infill density. Bump walls from 2 to 4 before you crank infill. Fourth, the 45-degree overhang rule is the geometric law of 3D printing. Anything past it needs supports. And fifth, the meta skill is to always name the technique with a specific number, not a vague adjective.